Very few people have came to class. Sure, 9, 8. Okay, anyway, I'm going to start the class. Yeah. In the last class, we have been discussing about the power definitions, some of the power system quantities, when we have been dealing with the harmonics in voltage and current also. And we are going to have the voltage quality. This is a unit which I'm going to start. So for in the earlier classes also, we have seen some of the definitions which have been related to the sources of sag, swell, unbalance, voltage unbalance, and harmonics, voltage harmonics. And also we have seen about the voltage quality standards which have been related to the harmonics. Okay. Effects of sag also have been mentioned about the effects of sag because yeah, and swell also. And then the voltage unbalance effects, what are the effects which will be going to be there in a system, okay, and the harmonics also. If you talk about the effects of a sag means, one thing I mean, every machine has been rated with the voltage, okay. If it is the voltage magnitude, if it is of a range of range of uh, the definition says of the sag is when you talk about the voltage sag, it says about the magnitude reduction of a zero point 0.1 to a zero point 0.9 per unit. Okay, 0.9 per unit. Okay, every equipment, every equipment has been mentioned the nominal voltage, nominal voltage, nominal voltage, nominal voltage plus or minus of 10 percentage of the nominal voltage. Okay, and obviously if it is the magnitude of 0.9 to 1 per unit, if it is anything less, anything in that range, then obviously the equipment is not going to function at all also. It's not going to operate also. Whatever the expected output is there, we may not going to get that output also. Okay. We are supposed to be maintain the nominal voltage of plus or minus 10 also. In that case, it is not going to operate. Even the voltage swell also, obviously the swell condition is of greater than of voltage swell is greater than of 110 percentage of the value. Then obviously the equipment mentioned voltage rating is of this. In that case, it is not going to operate also. Okay, that is the thing. But as we seen, this voltage sag and swell are related to a short duration voltage variation, short duration voltage variations with respect to the time. The time is the same as half cycle to 1 minute, half cycle to 1 minute. Okay, in this case, if there is any variation of the voltage between of 0.1 to 1 per unit within this one, if you have any kind of a backup system, if you have a kind of any backup system, then in that case your equipment is going to operate, or it is going to have a satisfactory performance also. Okay, as such, like we cannot I mean, if you want to study especially each individual load performance with respect to the voltage sag and swell, okay, what I mean to say that each individual equipment performance may depend on the internal structure or internal design of the equipment also. Uh, it is not, we cannot able to say that how does it the equipment is going to operate when we have the voltage sag and when we have the voltage swell. It is, we can't even predict the performance of any kind of individual load also. Okay, with this voltage sag and with this swell, the duration of half cycle to 1 minute. Okay, if you talk about the voltage unbalance. Okay, unbalance is there. In this case of the voltage unbalance, the typically it is going to have, if there is any voltage unbalance, okay, what I mean to say the voltage unbalance is due to the magnitude may not be the same in all the phases, or with the phase angle difference also there will be a voltage unbalance also. What I mean to say that you will be having one at an angle of 0 VA, and VB is also one at an angle of minus 110 degrees, and VB is also one at an angle of 110 degrees. In this case, these are all the magnitude wise it is 1 per unit. Magnitude wise it is 1 per unit. But may not be the phase wise, the phase difference is not equal to 120 degrees. It's not equal to 120 degrees. So this is the because of the phase difference is not equal to 120 degrees, also there will be a voltage unbalance. Okay, there will be unbalance even like the VA a zero point 0.8 at an angle of 0 degrees, and VB is 0.9 at an angle of 120 degrees, and BC is also maybe 1 at an angle of 120 degrees also, minus maybe it is take minus over here, it is minus 120 degrees. In this case also, in this case of these voltages also, you will be having the voltage unbalance. Okay, the voltage unbalance is due to the phase angle difference is not equal to 120 degrees with each other, and also due to the magnitude reduction also. Especially when you were, what kind of the effects will be there when you are going to give the unbalance. Okay, what kind of the unbalance will be there on the loads when you have been providing the voltage unbalance. Okay, one thing is for a single phase kind of a system, for a single phase kind of a system or single phase loads. Okay, in the single phase loads, when you give the unbalance, especially this particular value of the VB of a minus 120 degrees, if you give the VB, if you have been connected, VB is equal to 1 at an angle of minus 110 degrees, a single phase load, then in that case, the single phase load may not have any kind of an effect also, may not have any kind of a effect, because the IB current is nothing but the VB by whatever the load which has been connected to the base phase of the ring. Obviously, it will be having the current which whatever it is there, whatever it is there of IB, 1 at an angle of 120 degrees by ZB, or else IB, which is equal to 1 at an angle of minus 110 degrees by ZB. It's obviously the phase angle which is there with respect to the VB phase, with respect to the VB. Okay, whatever the currents of IB are there, IB currents are going to reflect with respect to the VB voltage. Okay, apart from that, there is obviously the required current is going to flow. Okay, required current is going to flow. And if there is any magnitude reduction, that is, uh, uh, yeah, if there is any magnitude reduction in the voltage, let us assume that it's a 0.9 at an angle of 120 degrees of by ZB. Then obviously you will be having a lesser current. You will be having the lesser current than what we have at 1 per unit, when we have a 0.9 per unit, obviously this IB current is going to decrease. What I want to highlight here it is the voltage unbalance is not going to very much influence the single phase kind of a loads also. It's not going to influence much on the single phase line loads. If you have a three-phase load, then there will be a problem when we have the voltage unbalance. Okay. One thing is you have a VA. This is VA, and then VB, and then the VC. Okay, VA, VB, and VC. Then we have here it is of ZLA, that is of ZLB, and this is of ZLC. Okay. Yeah. Here I drawn over here a single this is equivalent diagram also, maybe something like it is the voltage source is very far away and we will be having the feeder impedance also. Consider that these voltages are the VA is not equal to VB in terms of the magnitude. Okay, VA and VB is not equal to maybe is not equal, that is maybe around 0.95. This is equal to VA is equal to 0.95 and VB is equal to 0.9 and VC is equal to around 0.9293. Okay, these are the voltages. Okay, in that case what is going to happen is if it is a three-phase load, then obviously you will be having a circulating currents among the phases. ZLA and ZLB and ZLC is having a circulating current. Okay, that circulating currents is not at all required also. It's not at all required for the individual loads also. Okay, one thing, I mean, this particular circulating current you might be studying about when you're studying about the network theory. Circulating currents will be there when there is a voltage unbalance in phase A and phase B and phase C also. Suppose if you have a neutral current or neutral wire is going to connect over here, then obviously when you have an unbalanced current, in that case you will be having the neutral current. This neutral current is because of the neutral current is equal to minus of the IA current plus IB current plus IC current. It's simply like yeah. IN is equal to minus of IA bar plus IB bar plus IC bar. This is about the neutral current, which it is not required also. This is the neutral current which is existed. Basically, if you have a three-phase load, then the ZLA, I mean unbalanced load, ZLB is equal to ZLC. Okay, these are the loads which are being connected in the A phase and B phase and C phase are even the same also. In that case, if you have a voltage unbalance in A phase as the VB phase and VC, see, we have been considering this is the balanced load. This is the balanced load. We are looking over the problem of the voltage imbalance in a system. Here, what I'm just explaining was, I'm just explaining that what is the effect of the voltage unbalance in a system. Voltage unbalance in a system. If we have the voltage unbalance, then if I connected a balanced load in all the balanced load, a three-phase system, in that case, the current which is flowing of IA and IB and IC current are not balanced because of the voltage unbalance. Then your neutral current is going to have the flow of minus of IA bar plus IB bar plus IC bar. Okay. I mean, we can apply it at this particular point. Maybe if you take a capital N, we can find out the KCL. Okay, KCL at this particular node of N also. That is of the current which is here. The current is leaving, and the current of IA phase and IB phase are entering over here. Then obviously IN bar is equal to minus IA bar plus IB bar plus IC bar. This is a neutral current is unnecessarily, obviously it is a resistance is going to have, is unnecessarily overloading or producing the heating losses, which is not required also, which is not desirable also. This is one of the problem when you're been considering about the linear loads. Okay, I mean three-phase balance load also. Suppose in this case, if you connect an induction motor, if you connect an induction motor, okay, if we are having the unbalanced voltages of VA, VBC, and BC, what is going to affect? One thing is, uh, if you want to know the effect of voltage unbalance on the induction motor, then what we are supposed to do is we are supposed to resolve the voltages, the VA and VB and VC to the symmetrical components. That is the VA positive sequence and then the VA negative sequence and then V0. Okay. The VA positive sequence voltages, that is VB positive, VB positive and VC positive. These are the positive sequence voltages of phase A and phase B and phase C. These voltages is producing a rotating magnetic field. I'm just considering it is if the voltages are moving in this direction, okay, moving in this direction, the VA voltage, VB voltage, the rotating magnetic field is going to flow. Rotating magnetic field, magnetic field is going to flow in this direction. Okay. Then this is the rotating magnetic field with respect to the positive sequence voltages. With respect to the positive sequence, I mean, we need to look into exactly how the resultant voltages are moving with respect to the position or with respect to the time also. Okay, with respect to the positive sequence voltages, what I was telling you, the rotating magnetic field is moving in this direction. Okay, that is in the anti-clockwise direction. Now, if you take about a negative sequence voltages, negative sequence voltages, then obviously the negative sequence voltages have the phase sequence. You have been knowing about it also. How does the VA VBC looks like? The VA positive sequence and VB positive sequence and VC positive sequence. Whereas the negative sequence voltages are the VA negative, and this comes as VC negative, this comes as VB negative. These are the negative sequence voltage. For this case of the voltages, the rotating magnetic field is going to produce in the induction motor is in the this particular direction. That is a clockwise direction. Okay. See, this rotating magnetic field, I mean, is in the anti-clockwise direction due to the positive sequence voltages, and due to the negative sequence voltages, we will be having the uh, a clockwise direction. So this is producing one torque, that is a positive sequence torque, and this is about the negative torque. I mean, I'm just negative for the negative sequence, the torque is producing in the opposite direction. In this case, you will be having some kind of a pulsating torque will be there. Okay, having a pulsating torque when you have a positive sequence voltage, when you have the when you are exciting the induction motor with the voltage unbalance. Coming back to the zero sequence voltages, coming back to the zero sequence voltage. The zero sequence voltages are of VS0 and then the VB at 0 and VC of 0. These are not producing any kind of a rotating magnetic field because it's obvious, right? It is rotating, but the resultant always will be in the um, of the same magnitude. Basically, this kind of a zero sequence voltages is producing only the heating losses, only the heating losses in an induction motor. This is not going to produce any kind of a rotating magnetic field. Okay, and any kind of a rotating magnetic field also. Okay, this is producing the only the heating losses in an induction motor. This is one of the effect which you have to know, effect of voltage unbalance, voltage unbalance, voltage unbalance in an induction motor. Okay, will be induction motor. We'll be having the pulsating torque as well as the heating torque. These are the disadvantages because commonly we will be having the induction motor used for the water pumping applications. Because of the voltage imbalance, these are the things which have been going to occur in an induction motor. Okay. Um, these are the effects, and we have seen like what is the kind of the effects will be there in the harmonics also. In last class, I was mentioning about the power factor, right? With respect to the defining the power definition or the power quantities definition. I mean, power quantities derivation also. We have seen like the power factor is also is uh, going to decrease when you have the voltage harmonics. Okay. Yeah. Yeah. Next, we try to see about one of the thing is with respect we are whatever next in the next coming classes we are going to discuss much about whatever this content is there. This content is referred to the much about the voltage side. Okay, much about the voltage side, magnitude, magnitude. Yeah, we know that the voltage side. Just now we are seeing like when you talk about the voltage side. This is about the magnitude reduction for a duration of half cycle to a 1 minute. Apart from the magnitude reduction, apart from the magnitude reduction, if I draw the phasor diagram, this is about the VA voltage, and maybe this about the VC voltage, and this about the VP, It's about the PQI voltage. I mean, with the definition, what we have been understood was there is a magnitude reduction. There is a magnitude reduction. There is a magnitude reduction, uh, especially there is a magnitude reduction in the phase here by the definition. Apart from the magnitude reduction, you will be having the phase shift in the sag voltage. That is this voltage. This is the VA is a pre-sag voltage. Pre-sag voltage. Maybe I can represent this VA pre-sag, and this is VA sag voltage. Apart from the magnitude reduction, there is a phase jump. There is a phase angle jump or phase jump also. There is a phase jump in the voltage. Okay, in the voltage. But okay, why? Because why we will be having the phase jump in the voltage is, before going to that, this sag is going to occur is due to the fault in a system. Is due to the fault in a system. Fault in a system. Okay, this particular sag is also going to occur due to the induction motor starting also. Induction motor starting also. Okay. With respect to the magnitude wise, these are the things: fault in a system and induction motor. What is the reasons you have the phase angle jump? Phase angle jump. The phase angle jump is due to the XPR ratio. Due to the XPR ratio. XPR ratio of feeder impedance, impedance, and fault impedance also. Because now, when you have a fault occurred in a system, we'll be having about the fault current is going to influence by the fault impedance also. The phase angle jump is due to the XPR ratio of feeder impedance and the and fault impedance, and also transformation 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 of fault voltage from upstream to downstream. Transformation of the fault voltages. Here it has to come is transformation of the fault through transformer okay, from upstream to the downstream. Okay, we look into that aspects. How does this phase angle jump is going to have when there is a when we have the voltage sag, or when we have a fault also. Okay, the phase angle jump is also due to the fault only, but mainly depends upon the XPR ratio, and mainly depends upon the transformer also. Mainly depend on the transformer also. We look into the each individual aspect of this 1 and 2. How does the phase angle jump will be there when apart from the magnitude reduction in the voltage. Okay. Yeah. I mean, this is the definition of the, we are going to look into that, the voltage sag with phase jump. By the definition, this is the definition. Point 1 per unit to 0.9 per unit. The voltage sag is a reduction in the RMS value of the AC voltage between zero point 0.1 per unit to zero point 0.9 per unit at system frequency for a duration of 10 milliseconds to 1 minute. 10 milliseconds to 1 minute. Yeah, we have seen this part. What about the phase jump? Phase jump is defined as the phase angle difference between the voltage during the sag and the pre-sag voltage. That's what I was mentioning about. The pre-sag voltage, I have drawn it over here, and this is the sag voltage. This is the phase angle difference between the voltage during the pre-sag voltage, during the sag voltage and pre-sag voltage. This is a phase jump, uh, mainly occurs in a distribution system due to XPR ratio of the transmission line, and transformation of fault from higher voltage to lower voltage due to the type of transformer connection. Due to the type of the transformer connection. This is one of the point of X by R ratio. The second point, because of that, we'll be having the phase jumps. You can refer this particular paper, uh, this paper, the influence of transformer winding connection on the propagation of voltage sags, which is published in IEEE Transactions on Power Delivery. This is the volume, and this is the year. Okay, the influence of transformer winding connection on the propagation of a voltage sags. Okay, I'll try to illustrate the phase jump with the equation how does it is going to influence also. Firstly, I'll look into that the phase jumps due to expiration. For this is about a typical single line diagram. We have the voltage source and feeder impedance Z bar S, and then this is the fault impedance, and this is the load. This is the at the point of common coupling. I was just mentioning about the V sag also. You can, instead of V sag, we can take over as the PCC voltage also. PCC voltage. See, we are interested in finding about this particular voltage, a phasor, that is a V bar of sag or PCC during the fault. During the fault. Okay. Yeah. This particular we are deriving this the PCC voltage or the sag voltage when there is a fault. Okay, this simply simple by the voltage divider rule also. See, when there is a fault occurred in a system, this load current is very small also. This load current is very negligible. I mean, it is very smaller than your the fault current. Okay, neglecting the load current. Then what will be happen to the fault current? The fault current IF fault. See, we are interested in finding out this particular voltage. This particular voltage. Okay, the sag voltage. Okay, this is the phasor. Once you find out the phasor, then you can say that the PCC voltage or the sag voltage is having the phase. Okay. In order to find out the sag voltage, firstly, what we are finding out is we try to derive the fault current. I bar fault is equal to E bar. E bar is a reference voltage. Is a reference voltage. That means what I mean to that, the E bar is this particular at the zero. We are taking this E bar as a reference, then the I fault current as I fault is equal to E bar fault by ZS bar plus ZF bar. Now, when you find out the I fault is equal to E bar by ZS ZF, we find out the fault. If you want to find out the V sag, then what the equation is? The V sag voltage, the V sag voltage, the V bar sag voltage is equal to E bar minus of I fault current into Z bar of S. If you're subtracting the drop which will be there on the ZS, then we can find out the V sag voltage. Once you substitute this particular equation in IF, then what we get was we are going to get as V bar sag or PCC voltage is equal to ZF bar by ZS bar plus ZF bar into E bar. If you take this particular E bar as a reference, that is the E bar is equal to 138, and it is a reference also. What is going to happen is we're going to get it as the V bar sag or PCC voltage is equal to ZF bar by ZS bar plus ZF bar. Okay. Then obviously the phase angle, if you want to find out what will be the phase angle, we can find it also. What is the phase angle? It is this particular equation. This particular equation. The tan inverse of XF by RF minus of tan inverse of this particular ZS plus ZF, XS plus XF by RS plus RF. The ZS is the source impedance, whereas ZF is fault impedance, RF by plus JF. The ZS has RS plus JXS. Then in this particular equation, when you see that this is the equation, then obviously the sag voltage is having the phase jump. The phase jump also. That's what I was mentioning about the voltage sag phase jump. The voltage sag phase jump is dependent on the X by R ratio of the source impedance and the fault impedance. The fault impedance is between the PCP and then the fault also. Okay, what I mean to say that this ZF, this particular point, the fault impedance is between the PCC and the fault. From the PCC, the fault location is also dependent. From the PCC, if you look into this diagram, from the PCC, this is the PCC. From the PCC, the fault occurred is even the very far away, even it near also. In that case, the fault impedance is also going to vary. The important observation is the phase angle jump is very much influenced on the fault impedance or the wherever it is dependent on the fault location also. Okay, it is dependent on the fault location. The important point is the phase jump in the voltage sag magnitude is due to the X by R ratio of the feeder impedance as well as the fault impedance. Okay, with this equation, it is clearly understood also. And now this is the equation from the equation of 2.1. From the equation of 2.1, we have represented as when you take about the ZF is equal to per unit impedance or per unit length impedance of Z bar into the length. Length is the fault location from the PCC. With this equation, what I substitute is ZF as Z bar into L. That is Z bar into L, ZS plus Z bar into L. This, the source impedance is not going to vary. The source impedance is not going to vary. Only thing is the fault impedance is going to vary. The voltage sag magnitude is influence of this, the location of the fault also. Or else what I mean to say, L is the distance between the fault point and the PCC. Okay. So the fault is occurred very far away from the point of common coupling. If the fault is occurred at far away from the point of common coupling, that I can say that's V1. The fault occur at at PCC. At PCC is the V2 voltage. When you compare this particular voltage of V1 and V2, which one will be the lower? Fault occurred at the PCC have more severity, or the fault occur, in terms of the voltage sag magnitude, in terms of the voltage sag magnitude, in which of the case, either case 1 or the case 2, when you compare the voltage sag magnitude in the case 1 and case 2, which one is higher also, or which have the lesser influence in the voltage sag magnitude picture? I say is the V1, when the fault occurred at very far away at PCC, it has a less severity, less severe in terms of the voltage sag magnitude. In terms of the voltage sag magnitude is less severe than the fault occurred at the PCC. This fault occurring far away of PCC because the fault, when you look into this equation, IF is equal to the PCC voltage by ZS plus Z into L. Then obviously if your length is more higher, the length fault occurrence is very far away from the PCC, then this impedance is very high. Then what will happen is the fault current is going to decrease. If the fault current is going to decrease, then the drop is also going to decrease. Because of that, the voltage magnitude is very, the voltage sag magnitude is having a severity is very lesser than the fault occurrence at a point of common coupling. Okay. Even like in a distribution system, suppose if the fault is occurred at your home, in that case, at the distribution level, it doesn't even kind of at the distribution transformer, it doesn't have any kind of an influence in the magnitude reduction also. Okay, what I mean to say that if the fault has been occurred in your house, then that magnitude reduction is not going to influence the distribution transformer also. Okay, because the fault has been occurred very far away from the distribution transformer, and also the fault impedance is also very higher also, because at a PCC what we are when you look into this equation, when you look into this particular diagram also, you can understand it also. Okay. When the fault is occurred at the far away from the point of common coupling, then obviously the fault impedance is very much higher. Then what will happen was this fault current is very less. Then this particular drop is, when the fault current is low, and the drop is also very lower also. We'll try to look into these particular aspects of the fault impedance related kind of a uh, related studies also in the next coming class. How does this the fault impedance is going to influence the voltage segment? Okay, one thing like this is one of the equation, especially because of the X by R ratio, we will be having the phase uh, in a voltage during cycles. Now we try to see that one more another case, phase shift due to the type of the transformer. Due to the type of transformer. When you say about the type of the transformer, it is related to a three-phase system. Okay, obviously we will look into that the transformer. Uh, we have to look into the study with the three-phase transformer. We have the different types of the uh, transformers. These are basically due to the winding connections. The different transformers possibility is due to the winding connections. You might have studied in your EG courses, three-phase transformers. How does the winding connections is going to have the star star and star delta, delta delta, and delta star. Apart from these particular transformers, we have a dy1 and dy2 and dy3 and so on transformers also. This 1, 2, and 3 are, are with respect to the dot convention. These are the things which are you might be studying the you might be studying in your PG also. Even like this particular, I'll provide a paper also for you. How does uh, we are going to know about dy1, dy2, and dy3 also. I just yeah. This particular paper, this is the 50th paper, right? This paper, you can note on this particular title also, three-phase transformer winding configuration and different relay compensations. You can understand like how they are going to make about a D by 1 or D by 2 or D by 3 kind of a transformer with the winding connections. You can really get a much more clarity also when we try to refer this paper. Yeah. Now we try to see about how does a transformer is going to have a phase shift. For that, we consider a Y by 0 transformer. When you say this capital Y is represented to the a primary side and small y is a uh, secondary side. Whereas this 0 refers to the there is no phase difference between the primary voltage and the secondary voltage. So the 0 indicates the primary voltage is in phase with the secondary voltage. Okay. Now we have a Y transformer, a Y transformer, a three-phase transformer, and there is no neutral over here. There is no neutral grounded also. It is ungrounded transformers. It's an ungrounded transformer. Ungrounded both the secondary side and the primary side. The three-phase voltages on the primary side, I consider a single line to ground fault has been occurred in one of the phase. Now the VA1, VA phase, VB phase and VA. VA1 is the primary side. When I consider a single line to ground fault, it is a dead short. This obvious it is 0, 0 at an angle of 0. The VB1 is 1 at an angle of minus 120. And VC1 is 1 at an angle of 120. These are the voltages on the primary side during the sag or during the fault also. Okay, during the sag or during the fault. Now, I was mentioning about whenever you are going to study about a three-phase system, any unbalanced voltages, you have to look into the symmetrical components. For that, what I did was the VA1 voltages, VB1 voltages, and VC1 voltages converted to a zero sequence, positive sequence, and negative sequence. Okay, with this symmetrical component only, we can understand that whenever there is a fault occurred in a three-phase system, and the fault is transformed from the to the transformer, we will be having a phase shift also. For that, we are going to see that also. See now, these voltages, are converted to the zero sequence, positive sequence, and negative sequence. You can use this pattern equation also. You'll be knowing this equation also. Now, when you substitute over here, it is of 0, 0 at an angle of 0, and 1 at an angle of minus 120 degrees, and 1 at an angle of 120 degrees here. Once you substitute that and solve this equation, these are the VA1 zero sequence, and VA1 positive sequence, and VA1 negative sequence. These are, one is represented to the primary side. We are there in the primary side voltage only. Primary side voltage only. Now, we need to convert to the secondary side of the transformer. One thing is, when you are having this particular transformer, because there is no neutral, there is no grounded transformer. So then obviously, this particular zero sequence voltages is not going to flow from the primary side to the secondary side. Because the zero sequence gets open also. It is not going to have a flow also. That's what we have been studying in your symmetrical component theory. Symmetrical component theory for the different types of the transformer. For the zero sequence voltage, there is no transformation from the primary to the secondary side. Okay. Then obviously here, written here, in Y/0 type transformer, the zero sequence quantities will not transfer to the secondary side as neutral does not exist. One more point. Since this type of transformer connection will prevent the flow of zero sequence quantity. Secondary side zero sequence voltages here, secondary side voltage, that is VA2 naught is equal to 0. VA2 naught is equal to 0. That's why we are just finding out the secondary voltage. The VA2 naught is equal to 0 means that is because it is not a neutral connection. So because of that reason, the zero sequence voltage is not going to flow from the primary side to the secondary side of the transformer. Coming back to the positive sequence and negative sequence voltage. The positive sequence and negative sequence voltages are same as that of the positive and negative sequence voltages of the primary side of the transformer. Okay, because we have a transformer of VY/YY0 transformer. So because of that reason, the voltages, whatever we got the primary side voltages of the positive sequence voltages, the negative sequence voltages, you can take as it is. Now, the VA2 naught, VA2 positive sequence, and VA2 negative sequence, VA2 negative sequence, here it is 0, VA1 positive as it is, and VA1 as negative. Now, these are the voltages on the secondary side. VA2 0 as 0, VA2 positive sequence has this 0.67 at an angle of 0, the VA2 negative as 0.3 at an angle of minus 180 degrees. These are the voltages. Now, we got the secondary side, the positive sequence and the negative sequence voltage. Now, we have to inverse it to find out the VA2 not VA2 voltage and VB2 voltage and VC2 voltage. Yeah. Now when you transform this with this equation, substituting here, these are the conversion of a positive sequence, zero sequence, positive sequence, and negative sequence to the normal voltages. This is the transformer. This is the equation. Now, when you substitute here, the voltages of this 0.67 at an angle of 0 degrees, 0.33 at an angle of minus 180 degree. You substitute in this particular equation, 2.7, we will be getting this, the VA2 as this voltages and VB2 as this voltages and VC2 as this voltage. We can observe here what we got the VA1 was. I'm just winding up within 3 minutes. Okay, VA1 as 0 at an angle of 0 degrees. The VB1, what we got is 1 at an angle of minus 120 degrees, whereas VC1, 1 at an angle of 120. These are the primary side voltages. These are the primary side voltages. Primary side voltages. When you look into the secondary side voltages, these are the secondary side voltages. The secondary voltages, when you observe the B phase voltage, when you observe the C phase voltages, apart from the magnitude reduction, there is a phase jump with respect to the pre-sag voltages. The pre-sag voltages may be 1 at angle of 0, 1 at angle of minus 120 degrees. This 1 at angle of 120 degrees are the pre-sag voltage on the secondary side also. But when you see the sag voltages, this is the minus 120, whereas we got here it is minus 100.89 degrees. There is a phase shift of, it is going to have maybe this particular, maybe if I draw the phasor diagram, how does it looks like is, these are the phasor diagram. When you look into this, please, is it visible? Yeah. Yeah. Especially when you see this C1 phase is this voltage, VC1. VC1 is 1 at an angle of 120. Whereas VB is having a phase shift. This phase shift is there. The phase shift is there. It's 0.88, 1 at 100 at an angle of 0.89 degrees. 0.88 at an angle of 100.89. When you see the VB2 phase, the VB2 phase is also, earlier it is 1 at an angle of 120, minus 120 degrees. This is having a 0.8 at an angle of minus 100.89 degrees. When you see the VA2 voltage, the VA2 one is 0 on the primary side. The secondary side is VA2 is equal to 0.33. With this example, you can understand that there is a phase angle jump due to the type of the transformer connection or due to the transformation of the fault from a higher voltage to the lower voltages to the transformer. In that case, we'll be having the phase jump. Yeah. In the next class, we'll try to look into one more example also, and then also we'll try to see about how does fault location is going to influence the voltage side components. Okay. You will be having the minor one examination on this coming Friday.
Yes, sir.
26th. Okay.
Yes, sir.
Mostly the exam may start at 6, sir.
Okay, sir.
Maybe, actually, there is one more lecture is there. The popular lecture is there from 4:30 to 5:30. I don't exactly know the timings also. Once the presentation or that is over, only we'll be having the examination. Maybe the exam
Okay,
may
sir.
start at even at 7 also.
Okay, sir.
Okay, thank you.
So also one thing, sir. Excuse
Yeah.
me, sir. Sir, when we have to submit our class notes?
Yeah, I will clearly mention in that presentation, right? In the beginning
Yes, sir.
class.
Yes, sir. I'm just asking, sir.
Maybe around you will be 3rd of the 3rd of March.
Okay, sir. Okay, sir.
You'll be having the 4th exams, right? The mid exams.
Yes, sir.
Yeah, you need to submit by 3rd.
Okay, sir.
Do you require any time also?
Okay, sir. Okay, sir.
Do you require any time for the submission? Hello?
Yes, sir.
Do you require any more time? I'm just asking you.
So if everyone is comfortable, then it's okay, sir.
No problem. It is, see, once I fix the time is on 3rd Wednesday, I mean 3rd March. If there is any delay also, I mean, I'll be considering it, but you may not be evaluated for full marks.
Okay, sir.
Okay, for a
Okay,
10
sir.
marks, I think so, the notes marks may be. If you are submitting the late submission, obviously your marks will be deducted for the late submission.
Okay, sir.
Yeah, thank you.